Hello, and welcome to Material ConneXion's quarterly materials review. My name's Dr. Andrew Dent. I'm Vice President in charge of material research here at Material ConneXion.
My name is Gayatri. I'm the materials manager and I help clients identify best material solutions for their needs.
My name is Jennifer Coppola. I'm a materials researcher and I research innovative materials to bring into our library.
Okay, so this time we're going to be talking about extreme materials. I'll explain a little bit more about what we mean by that, but at least want to let you know that we're going to be taking questions at the end of the presentation. So if you want to ask questions, feel free to enter them in at the chat box in livestream.com. You can also follow us on Twitter at MaterialCX and also use the hashtag MCXReview. Okay, so let's get started. When we source materials, which we do on a monthly basis here at Material ConneXion, we're always looking for the most innovative, the most interesting and new. But this section, we decided to focus on extreme materials. What we mean by that is not necessarily just those that are the fastest, the strongest, the lightest, but perhaps materials that can deal with extreme environments or are in some way able to perform differently in a particular way. So we've put them into three different categories. Our first category is to do with temperature and thermal regulation. So materials that can deal with either extremes of heat or able to deal with temperature in a particular way. The second section is one we called invisible, but it's more just materials that are able to seamlessly or undetectably deal with extreme conditions. And our third one is to do with surface. Materials that have properties that are just unexpected or extreme in some way regarding the actual surface of the material. So we'll get going with the materials. My first one, I think it's going to be Gayatri. So.
Yes, so actually before we get started with our first material, I'm just going to peel the seal of this one. So this is the last material of this category, but it just needs a few minutes for activation. So I'm just going to leave it there and we can start with our first one. So graphene is considered as a wonder material for modern era. So graphene is made from a material called as graphite, which is typically used in pencils. And what makes graphene unique is its structure. So basically it is a single sheet of carbon atoms. So just to give you a reference, 1 millimeter of graphite will contain roughly 3 million layers of graphene. So what that means that it is ultra thin, it's lightweight, it conducts better than copper, it is 200 times stronger than steel, but it is 6 times lighter than steel.
So basically an extreme material.
Exactly.
Okay.
So it has really extraordinary properties. It is also light transparent, so it absorbs less than 2% light, and it is impervious to different kind of gases. So it can also be used for sensing applications. So graphene by itself can be applied as a coating on like metal substrate just because it is mechanically strong, durable, and it is actually even stronger than its other members of the carbon family, let's say carbon nanotubes. Or it can be mixed with polymer, like thermoplastic polymer, in order to make a master batch. Then it can be used for different lightweight, high strength applications, for example, in sporting goods. So nowadays we have like tennis rackets which are made out of graphene, or we have like shoes, helmets, and even recently we have seen it in active wear. And what's the use of graphene in activewear is sort of it acts as a filter between the wearer and the environment. So it will keep you cool and comfortable throughout the year. And then it also actually reduces the friction with air or water. So it gives you really top performance. Because of its optical properties, graphene is also used, especially actually the researchers of University of Manchester has recently made world's first light bulb using graphene, which is supposed to be long lasting than LED. It is made using a more cost effective method, and then it is much more energy efficient. So we have seen graphene being used across a wide range of applications. And then the last one which I'm going to talk about is using graphene as a thermal interface material. Because it has excellent electrical and thermal properties, graphene can be used to extract the heat quickly from its source. So for example, nowadays all the electronic devices are becoming smaller and smaller, so we are putting much more electronic component on a single chip, which might lead to overheating, which you might have seen in some of the really high fast, your laptops. So how the graphene, because it's really flexible, lightweight, it can be applied on pretty much any kind of substrate, and it will help to dissipate the heat much more effectively. So it can be used as a effective thermal interface material as well.
So basically, this has got the fastest spreading in terms of thermal conductivity.
Exactly.
Nothing's faster than this. Okay.
Exactly. Yes.
Okay. Nice. So, I mean, okay, so it's used in electronics. Can I use it? Where else could I use it? Can I perhaps put it, let's say I want to transfer heat. Let's say I'm wearing a jacket or somewhere I want to stay warm in winter. Could I use this as a heating element to perhaps heat up this surface and then cover the entire rest of the surface with heat? So
Yes, definitely.
Put
It
it
can be
inside like a
used.
jacket or something like
Yes.
that? Okay.
It can be used as an inner layer or membrane of the jacket. Definitely.
Okay. Super lightweight. Okay, thank you.
Okay, so the next material here. So recently we have been seeing a shift in, for example, the automotive industry. Rather than using metals, we're seeing a lot of plastic being used underneath the hood of a car, for example. So the advantage of using metals in that type of application is that it can withstand very high heat. However, it is heavier than a plastic would be. So with plastics, under certain temperatures, it's going to lose a lot of the performance properties. So we haven't been able to use it in that type of application. But here, this is Formlab's called High Temp. It is a photopolymer resin used in their 3D printer. So this is the first 3D printed material of its kind that can withstand extreme high heat. So up to 552 degrees Fahrenheit. 289 degrees Celsius. So that's the highest that we've seen. So imagine that's even higher than the silicone that you're going to be using, baking in the oven.
Right, okay.
So that can be used for more so industrial applications, of course, automotive, things where you're going to need that extreme heat to protect from that.
All right, so you've got a 3D printed material, but it's got the heat of a silicone, so it's ovenable. You can put it in an oven, it'd be fine.
Exactly.
Okay, so unlike silicone, this seems quite stiff. This is it's meant for sort of performance applications,
Exactly.
engineering applications? Okay, and I can print it like I would like standard photopolymer material, so I can print sort of all sorts of different designs and effects, but with a high heat material.
Exactly.
Okay, nice.
So the last material in this category is actually a self-heating solution. So what we have here in the package, which I opened a few minutes ago, was actually a chocolate bar. And within a time span of 2 to 5 minutes, it has actually, when I peel the top layer, it got activated because of air. So what we have here is a portable, powerful heating solution, which is self-contained. It can be used in the product or the packaging of the product for safe on-demand heat. So I'm just going to peel this off and we'll see if it is really hot and molten. Is everyone ready? Let's see.
Wow.
Okay, so basically I've gone from a cold chocolate bar through simply just ripping off that top surface. It's heated it enough to melt it, and now I've basically got chocolate, liquid
Molten
chocolate.
Exactly. So actually, this was my failed attempt to write MCX, as you can see it, but and you can actually touch it.
Okay.
It feels a little warm, but it's still quite safe.
Oh, you're right. Yes, it is. It's almost like a hand warmer. So how is it different from a hand warmer?
So the way this technology works, actually, this is developed by Exothermic.
It's totally liquid now.
Yes. So it actually harnesses the energy from an exothermic reaction of zinc. So
Okay.
when zinc comes in contact with oxygen or air, it actually oxidizes and it gives out energy or heat. And that's been used in order to heat it. So you can actually, it smells like it.
Smells so good.
So I will just leave it here for now. So actually, you can design it in a way to have like activation period anywhere between 2 to 15 minutes, depending upon the size, shape, what kind of power or the temperature you need it to be. And then it's very safe. All the materials used for this packaging, you can actually dispose it in your household trash.
Okay.
And if you separate it, you can also recycle them.
Oh, nice. That's a
It
good
doesn't
option. Yeah.
give out any dangerous or toxic byproduct during the heating reaction. So only trace amount of steam is released, but again, it protects you from any unwanted heat, which typically will be observed in case of other portable heating solutions out there.
Okay. So it's safe for food. and stuff.
Exactly,
Okay, fine.
definitely. And it just needs air for activation. It doesn't need any kind of water, fuel, or flame to activate it, which typically are also seen as a necessity for other liquid-based portable solutions.
I see.
So obviously it is much lightweight, so it will give you like thinner and compact product designs, and it will give you sort of instant heat anytime, anywhere you want it.
So other than chocolate, I mean, that's a great application, but what other types of packets would you be using that for?
So actually it can be used for any type of packaged goods. So for example, you can you can use it for a more like sort of local heating, so it can be used in sort of gloves or socks or even in your winter jacket in order to have more local heating. Or it can also be used in cosmetics in order for have like a particular hair care solution which needs to be heated instantly before using it. So you can use it for that application as well.
Like a hair mask.
Exactly.
Okay.
So it can be used for really wide range of applications apart from just like food and beverages.
Okay, so I can have like good hair care and also warm chocolate in extreme cold environments.
Exactly.
Okay, good. Okay, so those are the first three that constituted our first section to do with temperature. We're now going to move on to our second section, which is more to do with seamless or invisible. It's an approach to extreme that's really looking at how do we use materials to almost remove materiality. How do we make it thinner? How do we make it less obvious? How do we remove materials to make things more functional without necessary bulk? So this is our second section. And the first one for that is actually a glass ribbon. It might be a little hard to see, but I'm going to try and show as best I can. So you know that we've started to see flexible electronics and the use of glass in those flexible electronics. So we know that it's possible to make glass in very, very thin sheets. We've seen this with your iPhone, with your laptops. We've seen it in the start of wearables where it's possible to get very thin sheets of glass. That's done by a process which it liquefies the glass and lets it fall down in a sheet, and then that just gets removed. So in the same way that, say, treacle would flow from a hot treacle, or even sort of hot chocolate would drip down, you can do that within a sheet and create a very, very thin sheet of glass. So that process has now evolved into making incredibly thin tapes of glass. And I'm not sure whether you can see this. It's possible to see it. It's a very, very thin tape. I'm going to wobble it. So basically, could you normally do that with glass? No. It's basically become very, very flexible to the extent that I can now tie this into knots. So this is a thin tape of glass, probably only a few microns thick. It has durability like glass, scratch resistance are the same, but now it has the ability to be almost woven and knitted almost as a fabric would. The way they can do that, and the most interesting thing is that they're producing the tape in the same way they do the thin sheet of glass you typically do for making screens and things like computers. But what they do is they flame heat or treat the edges. When you treat the edges, you kind of seal them off. Once you do that, they become incredibly tough and resistant. So I can now sort of bend and flex this glass like a piece of yarn or plastic tape, yet it has all the heat resistance and properties of a piece of glass. Applications, that's the tough thing. We're not actually sure what they want to use it for yet. I mean, obviously, it's not wide enough to be used as a screen, but they are sort of, it's really only just been developed, so they're open to what we could use it for. So any sort of ideas, we'd love to hear those. If you want to actually put those into the chat box, any great ideas for incredibly thin, flexible glass, we'd be happy to hear them. But really, it's an extreme material in terms of the lightweight properties of glass, changing the way we think about that material.
So it can be used for maybe decoration, like a normal traditional ribbon you will use it. I don't necessarily know that.
That would be an extreme example of that use, certainly, yeah. One can imagine also, can I use it as, well, one of the original applications was as a incredibly accurate separator for certain medical devices. So I need to make sure that I have two pieces of material that are separated in a very accurate way, but this can also be autoclaved or heated up to make it sterile. This is a material that you could use, whereas most plastics you couldn't because they would melt. So that's one application, but it's really relatively limited. So we're looking for new uses for it. Okay.
So the next material we have here, so imagine an unpleasant smell in your home. And maybe it's from your dog, maybe it's from someone that smoked a cigarette inside your house, and you want to be able to remove that. You're never officially able to remove the scent completely. You're more so just masking it with something like a Febreze,
okay, yep.
Just like a room spray that's just going to kind of combine with those other odors and create a completely different odor.
Right, okay.
So an effective way to remove it, here we have a Veho. This is an odor removal solution. So what I've done here is I've sprayed these 2 non-woven sheets, and I have coffee in the jars below. So this is untreated. And this one here has been treated, so you're not able to smell the coffee through this sheet, but you are through here. So if you want to take a...
Okay, so this one is basically you've got almost like a piece of tissue paper, right?
Right,
Okay,
exactly.
and you've coffee in the bottom, and so what should I be able to
do you
smell
smell?
from it? I can smell nothing.
Right.
Okay, so this is the one that has the material.
Yes.
Okay, so that one, so I can smell nothing. Can I smell that one?
And that one you'll be able to smell the coffee.
Okay, yes, clearly
Yeah.
smell coffee.
You can clearly smell it, right.
Okay.
So what's it doing essentially is attacking the odor-causing compounds, and it's converting it into non-odorous scents. So what's great about it is that it's going to take away those bad odors, but if you have positive smelling, positive scents within your home, it's going to keep those without attacking those odors as well. So imagine when you use baking soda inside of a fridge, you're going to have to replace it every so often because
Right, sure.
it absorbs the odors. So this has no capacity. So you can really spray it in anywhere in your home, say your trash can, within your refrigerator, different areas within your house, your couch, to really remove those odors, because it binds the odors and completely removes it from those materials or those areas within your home, without taking away the positive scents within your house.
Okay, so if I've got, say, like a lavender fragrance, it's not going to attack that.
Exactly.
It's basically just going to attack the sulfur and those sorts of compounds.
Exactly. So it depends on the types of odors that you have in your home, whether it's oxygen-based, sulfur-based, nitrogen. So you can really cater it to those types of scents. So this would be customized based on the types of scents that you're trying to attack or remove from the home.
Okay. And
Is it food? Sorry.
go ahead.
Is it like food safe? Can it come in contact with food and still?
That I'm not too sure about. It's really supposed to be meant for areas, say your trash can, where it's going to be absorbing a lot of odors over time, and you really want to kind of remove those as you're taking out the trash, and it's not going to kind of smell up those areas. So this is something that you can use where it's really going to just kind of remove those scents away and then keep the positive scents within your home.
Okay, so compare it to, let's say, an antibacterial, antimicrobial. I mean, can I use? Is that an alternative to that?
Not necessarily.
Okay.
I just think that it would be more suitable for areas that you really want to just take away those odors from your home.
Okay. Yeah. Thank you. Okay, so for those of you who just joined us, you're watching Extreme Materials, Material Connections Quarterly Materials View. My name is Dr. Andrew Dent, and this is Dr. Gayatri Keskar and Jennifer Coppola. If you want to ask questions, feel free. Underneath there's a chat box for livestream.com where you can ask questions there, and also you can follow us on Twitter using the handle MaterialCX and use the hashtag MCXReview. Okay, so we're still on the second section, which is to do with invisible, seamless, or materials that reduce their volume by making them more lightweight in that sort of method. Okay, so our next one is.
We still have one more to
Okay,
go.
yes. Well, our next one is in what we call intelligent material. Yes.
Yes. So actually, counterfeiting, I don't know if you guys know, is over $600 billion industry. So this means
Fake stuff.
Yes,
Okay.
exactly. So this means more often than you think you will come across like fake Gucci or Louis Vuitton handbag.
Right.
And this not only results in huge financial losses for this high brand, but also actually destroys their brand image. And so I have something which is really simple and cost-effective solution, which is based upon something which is extremely small. And what is this is quantum dots. So I know the name sounds a little high-tech, and it is actually high-tech, but the way it works is very simple and easy to understand. So these are made from rare earth oxides. So contrary to its name, they are not rare, they are abundant, and they're not toxic. And these are like small crystals which, if you tune their size, shape, or composition, will emit different color light waves. So for example, this one
Okay,
I
so
don't know if you
what,
can
what are you shining at?
So this
What's
is a
this
laser.
thing?
This
Okay.
is a laser.
Okay.
And so if you shine a particular wavelength, you will see different color lights coming from
Okay,
these nanocrystals.
it's green. I mean,
Yes.
hopefully you can see that. It's actually quite green, the reflection. Okay.
Right. Then we have another one here. I don't know if you can see, but it's actually red.
Okay.
So how it can be used is it can be integrated in any kind of platform. So it can be integrated as a thread, which you typically use for the labels or even during the stitches on the bag itself.
Okay.
And the great thing is it requires in only small concentration, which is on the level of parts per billion. So it's not
Extremely
detectable.
small.
Exactly.
Okay.
So it is non-detectable at all. And so the only way you can detect it is when you actually flash a particular wavelength on it, and it will emit a particular wavelength of light, so particular color. And you can tune that color what you want it to be. So it can be used for something like different kind of products, which whether it is in the pharmaceutical or oil and gas or automotive, pretty much anywhere where you want to have that product security, brand protection, as well as consumer safety. So a consumer feels safe in order to buy these high-end products.
Okay. So I'm going to imagine a scenario. Okay, so I've got a couple of bags, but both I think are Louis Vuitton, and I'm wondering whether they're actually fake or not. So I simply just take my laser,
Sure.
and I shine the laser, and basically as I go across the stitching, they will glow green.
Yes. I mean, it could be any color as you
right,
want it to
or
be.
Okay, and the same
Exactly.
with drugs. If I'm working for the FDA and I'm worried about, I've got a whole bunch of generic drugs, this will basically cause that pill or drug to shine a specific color.
Exactly.
Okay, so what if I'm a very good counterfeiter, and I can find I purchase some quantum dots and I have a similar color. I can also do green. How do I differentiate between my green and their green? Is there I mean, once say Louis Vuitton has that particular color green, no one else has it?
So it can have that kind of sort of relationship with the brand itself.
Okay.
So you can have custom-made colors based
Okay.
on what you're looking for. And the great thing about the quantum dots that they give you really highly bright, pure, vibrant colors. So it's really difficult to mimic those colors with any other technology. So it's not something which you can just add different color pigments and make that kind of color. So
Okay.
that's the other thing. And so, sorry.
Can I show it again?
Yeah,
'Cause
sure.
I think it's interesting that, I don't know whether you can see this well, but the laser light doesn't show anything on my hand, but as soon as I go there, it goes green. If I put it on the top, which is also white, but it doesn't contain that, there's nothing. But as soon as I go there, it's green. So it doesn't show at all, then goes green. So that to me is the fascinating thing about it. Okay.
Okay, so other than, for counterfeit bags and things of that nature, what other types of applications are we looking at for this type of?
So as I mentioned before, that it can be used to make really highly pure, bright colors. So one of the other application is in LCD TVs or displays or architectural lighting. So actually recently, earlier this year, Samsung launched their super ultra high definition TV using quantum dot technology, which won actually Best TV Award. So it gives you OLED performance at LCD price. Because as I said, it is really a cost-effective solution, but it gives you a really bright or definite color range you wanted, and it consumes less energy compared to other technologies out there, because it has a really sharp color bandwidth. So you don't need to create different or high amount of that in order to get a particular color you're interested in.
Okay. Quite the wonder material.
Yeah.
Okay. So our next material is actually that's the last one of our second section, which is kind of invisible or seamless materials within Extreme. Our last section is to do with surfaces. What we mean by that is ways in which surfaces can withstand or perform in ways that are way beyond other materials. My first one is actually quite a standard looking material. Now, if you show this to anybody, they'd probably say, oh, it's a basic piece of steel. However, this piece of steel, because of the process it's gone through, is now actually stronger than aerospace titanium, has less volume, but actually is only about 10% the cost. The process is called flash Bainite, and it's a very simple process. It takes a sheet material such as this, and as the material passes through a particular bath, it basically heats up. the material heats up through an induction heating process to about 2,000 degrees Fahrenheit, so exceptionally high, really to the point at which this is almost getting molten. So around 1,000 degrees C, 1,200 degrees C, close to 2,000 degrees Fahrenheit. It heats it up in a line, and then immediately after it's heated up, it quenches it either in an air spray or a water bath. So the whole area, as it passes through this process, is getting heating up to incredibly high heats and then immediately quenched. In the same way that they used to quench swords as a way of improving the performance of ancient swords, they're now doing this on almost on a very specific level for the material. The advantage this has is it changes the microstructure, the sort of what's molecularly happening inside the steel, and changes its performance. So you go from a relatively basic type of steel. In this case, this material on a base level is not an expensive steel at all. It's a regularly sort of available, standard, low carbon steel. Through this process, though, it renders it into a high performance material. So if you look at this, so the material itself is not changed in any way. So in terms of the surface, it looks very much like the same material. But because of that, the performance of the outside skin really gives it that performance such that it then has the toughness and strength more like an aerospace titanium. So in the same way that sort of titanium has sort of dominated the aerospace industry, most airplanes have got, they went through from aluminum then through to titanium because it's so stiff and strong. This actual steel has the potential actually to form as an alternative to that, simply by that heat treatment process that it goes through. Okay, my next one is a very, very different type of material. This one's actually, and you may have seen examples of this, but we wanted to show this, can really sort of explain it properly. The material is called slips. And the idea is that it's almost biomimetic. If you think about the way in which, say, a lotus leaf is able to pass water off almost with zero friction, the way that the water itself rolls off the leaf. That process is done by, in that case, by little tiny hairs, which mean that the water droplet itself never really sticks on the surface. It just balls up and ends up on the hairs and just falls off. This does it in a slightly different way. What it does is it understands that any material, whether it's glass, in this case rubber, or plastic or metal, has a roughness to the surface. Microscopically, everything is very slightly rough. That, as a result, causes friction. So it slows liquids as they pass along that surface. So it increases friction, so it means that things don't move as quickly down that surface. What this stuff does, and it's been patented, is it puts an additional thin layer of a sort of liquid material on the surface. And actually, I'm going to pull this out and show, if I can. The actual surface of this material is actually it looks kind of glossy. It's actually a slightly sticky surface. But what that does, though, it fills in all of the holes, so that when a liquid, whether it's an oil or water, passes along that surface, it has zero friction, or virtually zero friction. A good example in application is, we've seen examples where if you coat this material on the inside, let's say, of a bottle of mayonnaise or ketchup, once you squeeze the bottle out, everything comes out to the last drop. There's nothing left in there as well. So it's a coating that can be applied to the inside of packaging. There are other applications as well. One of the most fascinating for me is if you think about the amount of energy required to transport water or oil or any liquid through a pipeline. If you've got a pipeline that's perhaps 20 miles long, the amount of energy required to move that liquid through that pipeline, because of friction, just because it's a pipe and it's made of steel, or even if it's coated with, say, Teflon, still has friction. So the challenge is, well, then you need to have a huge pump at one end to start pushing that liquid through. And the longer the pipe, the more force you need, the more energy is required. Because this has zero friction on it, as soon as you start that liquid moving, it just keeps moving. And therefore needs virtually no effort or energy required to push it through. So it has the potential to revolutionize industries where you're spending a lot of energy and effort moving things through a pipeline or along a surface.
So how it compares to other lubricating materials out there?
Well, yes, that's a good question. We have seen, and we have in the Material Connection Library, a number of sort of super hydrophobic surfaces. Now, you see those, if you actually have a look at what a water droplet does when it sits on that surface, it still contacts the material. Even though it's really sitting on top, it still actually has a contact with the rough surface. So even though it's a very limited friction, there's still some friction there because you've got contact between the water and the base material. The difference with this is that there's no, the liquid itself that's on the surface as part of the slips basically protects that rough surface, fills all the gaps in, and means that when the water rolls along, it virtually has no friction. So it changes that surface roughness much better than, say, something like a Teflon or even some of these super hydrophobic surfaces.
But then is it something that you have to sort of keep applying over a period of time? Will let it wear off?
Right.
Or?
Yes, because it's a liquid, there are challenges. They have different versions. They have versions which are very easy to apply by spray. You can hand spray them, but they have a limited lifetime. So one can imagine for applications where you only need for use maybe a few months, or it's just one application. So say a bottle of ketchup. That's possible to use a much more. The material itself doesn't need to be as durable, but they've now found a way that they can extrude or injection mold materials that contain this. So that then it's a lot more durable surface, so it can be used, it has a lot better durability, can withstand a lot more material passing through it. You probably need something like that for an application where you're going to be, where it's a lot more long-term and multiple use.
Great. So our last material, we've been researching Bent Black for quite a while now, and definitely one of my favorite materials that I have found so far. And what's important to note about it is that it is not a color, it's a material. So what it is tiny, hollow carbon nanotubes that are essentially, it's a forest of them. So it's not like a pigment or a paint where you can dip your paintbrush in it and paint your walls.
Okay.
It's really grown in a lab. So it's grown onto different substrates such as copper or aluminum. So essentially when light hits that surface, it's absorbing it like a black hole. So it is the darkest material that has ever been made. So it is sensitive to touch. It's really supposed to be encased in another material, so it's more so for industrial applications like aerospace. But it also can be used in accessories like watches where it's encased in another material. So although it is sensitive to touch, when it is encased, it's very robust when it comes to any kind of vibration or shock.
So basically, if I shine a light on that, there's no light coming back.
Exactly.
Okay.
Black hole.
So
It's lost.
So any sort of so we're talking about aerospace applications. Can you imagine sort of where else could it be used? Could it be used in can it be used in interiors? Can we use it inside, or is it just industrial?
So it typically, right now, it's smaller scale applications because it has to be grown on a specific substrate in a controlled area within a lab.
Okay.
So it is limited to the application as well as the size. So we haven't seen anything that has been commercialized in larger scale applications, but we're definitely excited to see what is available with this.
So explain to me again. Okay, so you mentioned that black isn't a color; it's just the absence of light. So
Exactly.
when light goes in, normally on a surface, let's say I don't know, my hand, the light hits it and bounces back,
Right.
and what's bounced back is the skin color. So what happens to the light? So
It's just completely absorbed.
it just goes in there and never comes back out again.
Yeah, because of the hollow carbon nanotubes.
Okay, so it's going into the nanotubes
Exactly.
and not coming
completely absorbed, and yeah,
out. So
it doesn't come out.
does it heat up? Because my thought is, if like light energy, if you shine a bright light on any surface, eventually it's going to get hot.
Sure.
And the more reflective it is, let's say it's a metallic surface, let's say it's the edge of this, it will shine back and therefore it won't get as
Right.
warm. That must heat up a lot then,
I can imagine so.
because it's absorbing all of that energy from the
Exactly,
light.
exactly. Yeah.
Okay. That's amazing. So basically, the most extreme, blackest material that's ever been produced.
Exactly.
Okay.
It's pretty exciting.
Thank you. Okay, so that concludes the third section, which was surface of extreme materials. We've actually got some, we've had some questions that have been popping up as part of our in our chat box, so we actually want to answer a few of those. So I'm just going to check my phone for ones that have actually come through.
In the meanwhile, as you can see, it is still pretty warm and pretty hot. Molten chocolate.
So that's stayed warm for 30 minutes.
Right.
Yeah.
Okay, so my first question is, how do you qualify extreme materials? I'll happily take that one. So Yes, it's easy to go out there and think about, what materials are the lightest and fastest and strongest, and those exist, and that's fair enough. But for us, what was important for us is really sort of thinking about the ways in which our clients might be able to use extreme materials. It's great to know about sort of the best, but also what are the extreme environments that our consumers might be interested in dealing with, whether it's extreme cold, whether it is extreme heat, whether there are conditions like extreme wear, those sorts of things. So you'll see, these materials wouldn't fit into a standard categorization of extreme materials, but for us, they're ones that are solution providers for the sorts of challenges that our clients have. So for us, extreme materials is always thinking about what do our clients need? People who come to Material Connection for solutions, how do we help them? And finding an uber expensive, impossible to use material is not so valuable to us. What is important are materials that can perhaps find solutions to extreme environments. Okay, we've got another question coming in. Okay, this one's actually for Jennifer, I think. Can Vanta Black be used in large-scale projects?
Definitely not large-scale projects, because currently at the moment it is grown within a lab onto different substrates like aluminum and copper. So currently it is very small and very controlled. So hopefully in the future that's something that we can look forward to.
Okay. I've got another one. Maybe Gayatri can answer this one. So, okay, we've seen a whole bunch of materials. These are in the library currently. So how do we, how would we get to see these materials?
So some of them are already in the library, but some of them, for example, this exothermic we just recently got this, so it's not yet live in our database. So hopefully soon, in span of maybe next couple of weeks, you'll be able to find more information about that in the database.
Okay, and we're going to have access to Vanta Black in the database as well?
Yes, we will.
Okay.
Absolutely.
Okay, great. Okay, well, thank you very much. I think that's all the questions we had. We had available. So thanks very much for joining us. And also, if you actually have any questions about this presentation or anything about Material Connection, please email us at info@materialconnection.com. So thanks very much for watching.